This is Lab 4 on oscillation. The purpose of this lab was to analyze the motion and energy changes that occurred in a spring mass system. We needed to compare the observed model to the predicted model to understand the connection between the spring's motion and the work energy principle. In this lab, we will be utilizing several important physics principles, which are Newton's second law, Hooke's law, which is the spring force, and lastly the energy principle. Newton's second law will help determine the relationship between the net force acting on an object and the change in the object's motion. With Newton's second law, we will use it to update the velocity and position of the data. In this lab, the net force acting on the system is equal to the spring force plus the weight force. Another fundamental principle utilized is the energy principle. The change in energy of the system is equal to work, where work is the transfer of energy between a system and its surroundings due to the application of a force. Since the system is a mass spring in Earth, there is no work done in the surrounding, meaning the total change in energy will be equal to 0. We can set the change in energy equal to the change in kinetic energy, which is the energy associated with the motion of an object, plus the change in gravitational potential energy, which is the energy that is stored due to gravitational attraction by the Earth, plus the spring potential energy, which is the stored energy when either stretched or compressed. The spring force equation is given by negative Ks times L hat, where S is L minus L naught. In Tracker, the calibration stick was set at 0.7 meters, which is the initial stretch of the spring. We will export the X and Y position data points into a CSV file so that we can then use that information to generate the computational model in GlowScript. Using the information found via Tracker, I estimated the period of oscillation in the Y direction to be 1.55 seconds. I will discuss in depth how I estimated the period of oscillation later on. There is also a formula which is t squared equals 4 pi squared times m over k, which is equivalent to t equals 2 pi times the square root of m over k. Using the period of oscillation, I was able to compute the spring stiffness using the rearranged formula that we just used to find t. K was computed to be 6.61 newtons per meters. Lastly, we needed to find the relaxed spring length, which we can find using Fg equals Fs, since we know that net force equals the force of gravity plus the spring force. Plugging in our known values, L naught was 0.104 meters. Some initial conditions that needed to be inputted was the mass, which was given as 0.402 kilograms. The initial position was found in Tracker to be negative 7.758 times 10 to the negative 2 in the x direction and negative 0.669 in the y direction. The initial velocity is the zero vector since the object was initially at rest. Next, I inputted the spring stiffness and the relaxed length of the spring, which was calculated in the previous slide. For the spring force, the L vector is calculated by subtracting the spring's position from the mass's position. L hat is calculated by dividing the L vector by the magnitude of that vector. Next, the formulas for the system energies needed to be inputted. These formulas are shown here to the right. The total energy is equal to the sum of the kinetic energy plus the gravitational potential energy and the spring potential energy. For the while loop, the initial energies were defined to be used later in the loop. The gravitational force is given by the following vector, where the y component is equal to negative mg. The spring force formula is negative k times L minus L naught times L hat. The net force acting on the mass is equal to the sum of the gravitational force plus the spring force. We can then apply Newton's second law to update the object's velocity and position, which is given by the velocity update and position update formula shown here. Using the new position, we can then update the spring force conditions. Lastly, the change in the energies of the system are calculated by inputting the formula shown to the right. The change in the following types of energies is simply found by subtracting the initial from the final values. In order for the model to fully generate, we need to import the CSV file containing the X and Y position data points from Tracker. In the model and graph, red represents the observed motion and blue represents the predicted. From the graph, we see that the observed initially resembles the predicted at the start of a time period, but as time passes, the observed and predicted motion start to deviate. This can possibly be accounted for if we discuss the drag force, which in this lab was negligible. The following graph displays the energy changes in the spring mass system. Since the work was done within the system, then there is zero work done by the surrounding. We call this a closed or isolated system since there is no transfer of energy to the surrounding. Therefore, it makes sense that the total energy has a constant of 0 as shown in the graph. We can say that the energy principle was indeed satisfied. Using the graphs generated from the data, we are able to estimate the period of oscillation, which is the time it takes for the mass to complete one oscillation. Using the x position graph, I found that it took about 5.13 seconds for the mass to complete 3 oscillations. Therefore, the period of oscillation is about 1.71 seconds. In the y direction, 3 oscillations took 4.65 seconds, and so the period of oscillation is 1.55 seconds, which is a little less than the period of oscillation in the x direction. If the two values were to have differed greatly, we would have two greatly different spring constants for the same spring. We use the time period in the y direction since the force of gravity acts downward in the y direction. Possible sources of error include human error when we manually track the center of mass in Tracker to get our position data points. Furthermore, the computational model is not as accurate as it would be if drag was accounted for in this lab. We found that the motion of the spring mass system was mostly consistent between the observed and predicted models. As a result, we were able to prove that energy was conserved within the system, and therefore the energy principle was satisfied and proven.